Last talk, I talked about observations, that we need to do multivariate observations, and I showed you images of galaxies, little bit of stars. Now I'm going to talk about my area of research, what I work in, galaxies and their interactions. The galaxies actually interact with each other, and I think this picture is an example of that. It's a very beautiful picture taken probably by the Hubble Space Telescope, and you can see two galaxies, and there is a stream of material connecting them. Sometimes this stream of material is visible in the optical, like it is now, but very often, even if they are further apart, we can see it in neutral hydrogen 21 centimeter emission. So galaxy interactions, we again have to use multi-wavelength observations to look at them. Now in this talk, I'll describe briefly about galaxies, about the two types of galaxies. I hope I'll be able to sufficiently enlighten you. But please again, stop me and ask questions, because in that way I know that I'm getting through to you. Also, I have a few slides on black holes, because I believe you were not given any lecture about black holes. So I've just included a few slides about black holes. I know all children ask about black holes. I think they know more about black holes than we do. Okay, so this talk, as I just mentioned, will focus on the different types of galaxies, and then I'll talk about the black holes. At the centers of galaxy, we don't have small black holes. We don't have black holes which are just the end state of stars. We have very massive black holes which are usually 1,000,000 times more massive than the sun. This is the definition of a supermassive black hole. A black hole which has a mass of 10 to the power 6 times the mass of the sun. So I'll talk about that. Then I'll talk also about galaxies, how they cluster, because as I mentioned in my previous talk, in the universe, the most dominant force is gravity, and gravity, as we all know, is an attractive force. It will try to always bring stars, planets, galaxies closer to one another, and simulations and observations have shown that galaxy clustering is a very important part of our universe. And lastly, I will show how galaxy interactions and mergers drive galaxies to change, to evolve. So let's now start. Okay, again I'm showing the Milky Way, so I think I'll skip this. Okay, this is an image of stars and galaxies, how you would look at in the universe if you had a camera which looked predominantly in the infrared and also maybe visible. This is maybe a composite of several wavelengths. So it's all very busy there, right? And you can see in the center it becomes even more busy. So you can see here in the central part of this image, you can see a large clustering of galaxies. That's a galaxy cluster. But another thing, you can also see is that you're seeing different types of galaxies. For example, this galaxy looks like it's like a wheel. It's got a bulge in the center. But you have galaxies which look very spiral over here, and you have elliptical looking galaxies over here. So you have galaxies have different types of appearance. But basically, all galaxies are of two types. And I think that if you know a little bit about astronomy, you would know this. You would know that galaxies are of two types: elliptical galaxies and spiral galaxies. Spiral galaxies are called spirals because they have this spiral kind of structure on them. But what they are is also, they are disk galaxies. So now, since most of you have done science, you're physics teachers, you're, lecture in colleges, you have to look at it more clinically. So the difference between the two types of galaxies is their motion. The spiral or disk galaxies, in these galaxies, the stars are moving in a circle, and they are balanced by the centrifugal force and the gravitational force. So they're moving in a circle. That's the equilibrium. Those are the disk galaxies. Now the elliptical galaxies, however, as you can see in the image here, they have a very diffuse appearance. They don't appear to have any disk. Their equilibrium is not due to disk motion. In those galaxies, it's due to a more chaotic or random motion. I say chaotic or random, but actually it's due to orbits. Orbits which are not confined to a plane, but orbits which are moving in the potential. So if this is my galaxy as I see it, I'll have orbits in all kinds of directions. The net result will be a kind of pressure in the system which will oppose gravitational collapse. So we have two types of galaxies, disk galaxies which are spiral arms, and we have elliptical galaxies. Yeah, tell me. Yes. Yes. Huh. Yes, so that's a loop like this, like a loop. To go to the center and it'll have so much velocity, it can't stop and it'll continue like this and it will take a loop. But the loop may not always close. So it'll go up and it will miss its beginning and go another loop like this. So the loop will have a structure like this, a rosette. Yes, but it happens also in spirals, but only in the bulge. A bulge in the center of a spiral galaxy is like a small elliptical galaxy. So we'll talk about that. Yeah. Okay, good. So now we have two types of galaxies. That's pretty clear, and you can see they look very different. Now, what are they made of? Galaxies are made of stars. That's very obvious to all of us from my previous lecture. Stars means they can have millions to billions of stars. But it's not just stars. Galaxies are also composed of gas. The gas is mainly made up of hydrogen. Hydrogen is the main element in our universe. It's the element with just one electron, right? One electron, one proton. It's the simplest, and that's where the universe started from. So most of the universe is made up of hydrogen. So galaxies contain clouds of hydrogen, and the hydrogen can be of two forms. It could be neutral hydrogen, atoms of hydrogen, only single atoms of hydrogen each, or it can be pairs. It can be molecules of hydrogen. Okay, so molecular hydrogen, neutral hydrogen, this is the main gas in galaxies. And apart from gas, there is also R. Now, if you look very carefully at this equation, and this is a very simple equation that we use in the satellites. Oh God, this doesn't come inside here. So, do you remember this equation? Right, and this equation MR. So, in a galaxy, if using the ionized gas, we can measure the velocity at which the galaxy is rotating, right? And we know the radius, then we can find out the mass of the galaxy. So, MR, because MR is determined from the velocity in the galaxy, it is called the dynamical mass of a galaxy. This is very important. I want you to remember it. Now, the second thing is the elliptical galaxies. So, the elliptical galaxies have random motion of their stars, moving in orbits, but basically random in all directions. That gives a velocity dispersion. I think most of you know what velocity dispersion is. It's just standard deviation. Remember in class 10, statistics or maths, we studied standard deviation, which is v squared minus v average squared. That is equal to sigma squared. So the velocity dispersion can give you an idea of the pressure that balances the mass in the elliptical galaxies. So you see, we can obtain the mass of galaxies using their motion, and that is termed as the dynamical mass. Now let's say, let me write here on the board. Let's say I find out the dynamical mass of a galaxy. So I will say that is M dynamical, right? And then using my telescope and using all the measurements of the stars, I can find out the mass of the stars, right? I can find out the mass of the gas because I can use a multi-wavelength observations to find out the mass of the gas. Then I would expect whatever I got from V squared by R would be equal to M star plus M gas, right? So I would find that this I get from the motion V squared by R. Okay, so this would be equal to M star plus M gas. But about 78 years ago, there was a scientist called Zwicky from Caltech. Zwicky found that this is not true for galaxy clusters. There was another scientist called Vera Rubin. This wonderful lady who I met in the US many years ago, she also found that the mass from gas and stars does not equal the dynamical mass that we measure from motion. And that's simply because there is a mass in galaxies which we cannot see. It's called dark matter. Yes. Okay. So that's why M dynamical is actually equal to M star plus M gas plus dark matter. And this very simple result is something I use even in my work today. I use multi-wavelength observations to find out the dynamical mass, and then I use my optical observations to find out what is the stellar mass, gas mass, and I find that the difference is equal to the dark matter mass. So let's move on now to, since I've told you about the dark matter mass, I can also then explain the dark matter halo of galaxies. So let's now first look at the structure, say, of a spiral galaxy or a disk galaxy. We call it spirals because any disk galaxy usually has spiral arms. This is its anatomy. This is what it looks like. It's basically composed of a nice disk. This is the disk. There is a disk which is often having like a bulge in the center. So it has a disk with a kind of a sphere in the center. And then this structure, the disk and the bulge, is embedded in a very massive halo. The spherical structure is the dark matter halo. Now, you may ask me, if you can't see it, how do I know what it is? How do I know if it's a spherical halo? Dark matter, we can't see. The only way we know that dark matter exists is because it has a gravitational effect. Okay? So if I see that objects are moving, but I can't see what they're moving due to, then I know that there is some unseen mass there. And if I use good telescopes to look deeper and deeper and I still can't see the mass, I'll say that that mass is dark matter mass or it's missing mass. Now we still don't know what dark matter is, whether it is some particle physics kind of atoms like axions or WIMPs. We still don't know what it is, but we know it is there. So galaxies have a disk, have a bulge embedded in a dark matter halo. We don't know what exactly its shape is. Let's assume for simplicity it is spherical. Now in this dark matter halo, around the center of the galaxy, there are these compact clusters, and we call them globular clusters. Globular because globules are supposed to be round, compact, dense structures. So globular clusters are one of the oldest structures in the universe. They're like the dinosaurs. They are these small clusters which are distributed in the dark matter halo. So this is the basic structure of a galaxy, and the stars are residing in the bulge and in the disk. Yes. Yes, you can't see it. You only know it's there because, like I said, the mass, it's making the galaxy move in a particular way. Because in the outer parts of the galaxy, we can't see any stars, but there is gas moving in a disk. What is helping it move in a disk? Its gas is like the clouds in the sky. They will just evaporate, they'll just move away, but they're not something So there must be in the potential some mass which we cannot see. Transparent. Okay, so generally dark matter is supposed to be the main mass of a galaxy. There are some what they call low luminosity galaxies where the dark matter is like more than 90% of the mass of the galaxy. So in our galaxy, I think dark matter is maybe 90% the mass of our galaxy. Our visible matter is only maybe 10-20%. But I'm not sure of that number because we actually don't know where our galaxy ends. It's very difficult because we are sitting in our galaxy. Yes. Yes. So I will maybe, you have a question about dark matter? Ah. Ah. Yes. Yes, because a planet is embedded in a solar system or a stellar system, right? And that star is moving around the center of the galaxy. Yes. So let me just do one because I think it's nice to know about dark matter because it's like such an important part of our universe. Yeah, shall I just draw this and then I'll answer your question at the back? Huh? Okay. So we have talked that galaxies, spiral galaxies, these galaxies are having a velocity. It's moving like this. Suppose I now draw a curve and I am moving away from the center of the galaxy, right? This is R and this is the velocity. The velocity curve for any galaxy has this form. In the center it rises and then it becomes flat. Okay? Now suppose in a galaxy I have v squared by r equals to g m r, okay, divided by r squared, right? So mr equals to r v squared by g. You all agree? Simple. The satellite equation, right? Now suppose we go to the outer parts of suppose I'm going away from the center of the galaxy. Now there's no matter, right? Okay. But v squared mr is proportional to r and the v squared. So here there's no matter, so I'll expect the velocity to fall, right? I'll expect the velocity to fall because there's no mass there. I'm just moving away from a point mass, but the velocity does not fall. So the flat velocity of the rotation curve is due to dark matter. This is why we know that dark matter exists outside. Yes. Okay. So galaxies are moving and the rotation curve rises up and becomes flat. If there was no dark matter, the rotation curve should rise and then finally fall, right? Because after a point there are no stars, but it doesn't. We can see from the neutral hydrogen that the rotation curve keeps going flat. That means that there is some mass that is making the galaxy go round. And that mass is the dark matter. Density as we go out. In this figure, it varies from galaxy to galaxy. I can send you a reference. One of my papers I'll send you. You can find from there. Yeah. Someone at the back asked me a question. Yeah, tell me. Halo. What does a halo mean? Ah. Ah. So that's a very good question. See, I've drawn a dark matter halo, or the cartoon shows it to be spherical, but we don't know what shape it is. That is still a topic of research. And we don't know what is the dark matter, so we don't know whether the dark matter is like some uniform fluid or is it due to clumps? We don't know. So those are still open questions. So good questions, but yeah, I think no one knows. Yeah, tell me. The dark matter is six dimensions. Oh, well, in phase space, everything has six, position 3 and velocity 3. In that way, it has six, not dimensions, six coordinates in phase space, yes. But we don't know exactly what the particle is. So we don't even know how to really describe it. But yeah, in phase space, in position, it has 3 and velocity, it has 3 every place. Okay, so actually that was not part of my talk, but I think it's an important thing to know about dark matter. Now, so this is just a figure showing you how the neutral hydrogen is, arranged in galaxies. It's in the form of the disk. So here is the disk of our galaxy, which you can see here. And so the neutral hydrogen is in a disk. Now, when you have any gas or any fluid, the heaviest fluid will go to the center or to the bottom, right? So that's the same way with molecular hydrogen. If this is neutral hydrogen, this is molecular hydrogen. Molecular hydrogen distribution is more narrow because it's dense. So it settles to the plane of the galaxy. And you can see it's also very clumpy. That's how molecular clouds are in galaxies. They're very clumpy. And molecular clouds are where stars form. If you remember, Dipti talked about star formation. She was referring to star formation happening in molecular clouds. That's where they form. So this is the dust. The dust is associated with the molecular gas because dust particles are where molecules of hydrogen are formed. Because I remember, when we studied this, I remembered in school, molecules of hydrogen are very difficult to form in nature. You need a catalyst. The catalyst is, I think, platinum. But in the universe, it's the dust particles. So two atoms of hydrogen come and sit on a dust particle, and then they combine, they lose their energy and combine to form molecules of hydrogen. And these molecules of hydrogen form dense clouds in which stars are formed. So molecular hydrogen gas is actually the fuel for star formation in galaxies. Now, spiral arms are the most, I think, the most beautiful things that we first notice about galaxies. And spiral arms usually appear like this. This is, I should use this one. This is a molecular hydrogen map of a nearby galaxy. I think it is 101. And you can see how beautifully the spiral arms follow the molecular hydrogen gas. Now, this one is a cartoon of the spiral arms in our galaxy. And the sun is here. You can see the sun is here. And the sun is embedded, we are embedded in the Orion arm of our Milky Way galaxy. So Orion is not just an Orion star-forming region. Orion is a molecular cloud. It is our nearest molecular cloud. It is where the nearest massive stars are forming. But near the Orion molecular arm, you have Perseus arm, you have the Sagittarius arm, Cygnus, Centaurus. You have several spiral arms. So this spiral structure was determined by looking not just at the stars, but also looking at the neutral hydrogen images and molecular hydrogen images of galaxies. It's difficult to do because you see, we are inside our galaxy. It's very easy to look at the outside galaxy and notice the spiral arms, the star formation, but when you are inside the galaxy, it is really hard. So that has been very challenging. And elliptical galaxies, I've spoken a lot about their non-circular orbits, so I don't think I will talk much about this anymore. Now we'll move on to a topic where I think A lot of people have questions. I mean, students, I'm sure students will ask you a lot of questions about black holes. So I will just start by saying that a black hole is, according to classical definition, a black hole is an object where the space-time, the gravity is so strong that not even light will escape. Okay, this is the classical definition. If you remember from our satellite equation, the escape velocity, okay, escape velocity is given as v squared is equals to 2 gm by r. You remember, because that just simply comes from 1 by 2 mv squared minus gm by r squared is equals to 0, right? Energy is equals to 0, and we get the escape velocity from our Earth. Now, in that relation, instead of v as escape velocity, let's put it as light. Nothing can be faster than light. That we know. So let's put that as light. Then that c squared will give you the mass of the black hole. Whenever you come to any source in our universe where the velocity of the light that we are seeing is being redshifted more and finally becomes so redshifted that we say, okay, that the escape velocity from that source, that mass is approaching that of light, we know that there must be a black hole there. Now this is the definition coming from simple classical Newtonian physics. Nothing basically can come out of a black hole. But you see, when black holes were first thought of, they were not thought of as a source or a star dying in the sky. They had a more, what shall I say, more eclectic definition, more kind of mathematical definition. I think many of you here must be coming from mathematics background. So you will know that there is, in mathematics, there is something called the singularity. A singularity which Chandrasekhar talked about, a singularity is a black hole. Okay, so it happens when you have the singularity in space-time. Space-time means simple, our space-time, XYZ, but it can be curved, in which case there is a metric. Okay, space-time can be curved, and space-time has not just the physical coordinates, but it has time. So it has X, Y, Z, T. That's called space-time. Now, when the space-time we see space-time which is so curved that there is a singularity, we say that that is a black hole. And that black hole from mathematics we know also has an event horizon. It has a horizon beyond which we cannot go, because even light cannot leave from that event horizon. So there's a black hole, it has a mass, it can be related to the speed of light as escape velocity, and it has an event horizon. And that event horizon is also given by a very simple relation. We can talk about that later, but let me talk about the physical definition of a black hole. That was the mathematical singularity definition. The physical definition of a black hole is that it is the end state of a star, which was given by Chandrasekhar, who was also a very brilliant mathematician. But he linked the two. He linked the two, and he showed that beyond a certain limit, you will end up, when a star dies, it will leave behind a core, and when that core becomes very massive, it will keep on collapsing and finally become a singularity. So as I was explaining to someone in the audience, when you have stars, and let me see if I have a slide. Yeah. When you have stars, if you look at the left-hand side here, if they are very massive, not all stars are massive, but if it is very massive, then it will end up in an explosion. It will end up in a supernova explosion. Now, when this supernova explosion happens, the outer layers of the star are thrown out, and it forms a supernova remnant. But the central part of the star still remains in the core. And that core, depending upon the mass of the core, we will end up with three end states of stars. The first is the black hole. It's very massive. It just keeps on collapsing, 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 forms a black hole. Number two is a neutron star. It will keep on collapsing until its center becomes a superfluid, a neutron superfluid. And that neutron superfluid has a pressure, degeneracy pressure, and that pressure opposes gravity and it comes into equilibrium. Now, some neutron stars, not all, but some neutron stars give out emission from their poles, and that emission is called pulsars. Those neutron stars which give out emission from their poles are called pulsars. And so you can imagine a pulsar is like this ball which is rotating on its axis, and from the top, one of the poles, you're getting a beam of particles. And those particles give out radiation, which we mainly see in radio. So in India, we really love studying pulsars with the GMRT. So a good analogy is this, is that if you go to any airport, you'll see a light at the top, that's for the planes, and it goes round like this, right? And that beam of light will cross you only once, like this, then go back, then it'll come again, like this, right? That is a pulsar. It's like a lighthouse or a rotating beam of light. It will come across your line of sight only like this, then it will go away. Come again like this, then go away. So what you'll get is pulses. You'll get the pulse of light, pulse of light, pulse of light. And that was first interpreted as aliens. People thought, okay. No. It's all in radio waves. It goes through our bodies. But it's telling us so much about the universe. So it's great. Of course, yeah. Because remember the lighthouse? From a lighthouse or from, it's crossing our line of sight only sometimes. Suppose I have a telescope here, right? So I can catch the beam of light from a pulsar only when it falls in my direction. No, because it's rotating. So suppose some light is rotating, a torch is there, and it will cross my line of sight, right? Then it will go away. Huh? Pulsar. So let me show you the, okay. So this is the pulsar, right? It's rotating. This is the light, but it's crossing my line of sight only now. This goes away. Now it goes away. Spinning, yeah. So the pulsar, yeah, I forgot to use that word. Pulsar is spinning on an axis. And because of the magnetic field of the pulsar, and because it's spinning, we see a pulse. Okay? But not all neutron stars are pulsars. Not all of them. So, as I said, you can get a black hole. It's a star. After supernova explosion is very massive. You can get a pulsar. You can get, you can get a black hole. You can get a neutron star, which can be pulsar. And lastly, if the remnant is very small, or not the remnant, but if a star is very small, it will just kind of become a white dwarf. And a white dwarf has, so a white dwarf is also, it's an evolved star, and the star is collapsing, it's become old, it's used up all its fluid. And in the center, you get an electron fluid, an electron superfluid. That degeneracy pressure of that, the quantum field of that electron superfluid, that prevents gravitational collapse. So there are three end states of stars: white dwarf, neutron stars, and black holes. Okay, we've gone again. Is it? Okay. Oh, it just went off. Okay. Okay, now. So we've understood a little bit what about is the end state of a black hole is the end state of a. Now, What I just now told you was how a star forms a black hole. But the black hole, if it forms like this, will only be 3 or 4 times the mass of the sun. It will be small, kutti. But the black holes that we think exist in the center of our galaxy and external galaxies are several million times the mass of the sun. They're supermassive. So where did those come from? Okay. Now those we know they exist, but we still it's a very active area of research. How did supermassive black holes form? They must have formed from some seed black hole in the early universe, and then that black hole grew because galaxies merged and the black holes merged with one another. But we still have not understood how those seed black holes formed. But what we do know that yes, just like I've shown you in this image, the centers of all galaxies are having a black hole, a massive black hole. Now, even though I say massive black hole, the mass of the black hole at the center of the galaxy is very small compared to the mass of the galaxy. It's not even 1%. Okay, usually, for example, the black hole in the center of our galaxy has a mass of 4 into 10 to the power 6 times the mass of the sun, right? 4 million times the mass of the sun. But our galaxy mass is 10 to the power 12, right? So that's like a very, very small mass total of the total. So the most massive part of galaxies, I think you should remember, is the dark matter halo. But the black hole is at the center and it is routing the center of the galaxy potential. Okay. So how will this, someone was asking me about this question also, how do we see them? Black holes, how will we see them? It's a bit like dark matter. I mean, it's not giving out any electromagnetic radiation. How do we know it exists? And for many years, poor Chandrasekhar got a lot of doubts. No one really believed him. They thought it was some theoretical thing. But black holes in the 90s were found to exist. Now, there are two reasons why black holes are found to exist. Now, if you have a black hole, what it will do, its gravity will make the objects around it move in a particular way, right? So the black hole will make the stars move in either circles or loop orbits around it, right? A black hole may also swallow matter. And theorists many years ago showed that when matter falls into a black hole, the black hole doesn't completely swallow it. It tears it apart due to the large tidal forces. You all know what a tide is? Tide, right? Tidal force is nothing but the variation of gravity across any object. So we know, say, suppose an object has a mass of m, right? So the gravitational force across it is gm by r squared, right? Now suppose I do a differential of that ddr of gm by r squared. That will tell me how the force of gravity is varying across the body. Okay, that's tidal force. Now, when any star, for example, comes close to the black hole, what will happen is it will get stretched by the tidal force. The force of gravity at one end of the star and the other end will vary and it will pull it apart. So as a result, only some amount of the mass falls into the black hole and the other amount of the mass is thrown out. Now, the debris that is thrown out from a black hole, most of it is usually converted to energy. You all remember E is equals to mc square? You all know this, right? So you can imagine even 1 gram or even the mass of our sun, if you convert it into energy, that's a huge amount of energy. So that's why black holes appear luminous. They are not giving out energy, but when matter falls into them, then energy is given out. And that also brings me to another point, that black holes are not always swallowing mass. There are many galaxies which have very quiet black holes. We know they exist because we can somehow make out the stars are moving in the gravitational field of the black hole. But the black hole is quiet. It's not eating any mass. So you can't see any radiation from it. It's quiet. So this is the the problem. Not the problem, I would say. This is the difference between two types of black hole. The black hole that is accreting mass is said to be active. The black hole that is not accreting mass is said to be non-active. Active black holes are called active galactic nuclei, AGN for short. The ones which are not accreting, they're just called normal black. So I've more or less explained how we can see the effect of supermassive black hole, how we can see them. We can see them via the mass that they are swallowing. We can also see them by the gravitational force that they exert on the stars near them. So let me talk about one of the big Nobel Prize winning discoveries, 2012. So here, if you see, this is you can imagine this is a telescope looking at the center of our galaxy. If you remember, I told you that the galactic plane, which you'll see in the sky, at the center is the center of our galaxy. Now, the center of our galaxy, people had, in the mid-90s, they had identified a radio source there. They found that there's a radio light emission coming from there. So they said it's called Sagittarius A star. There's something happening there. A lot of radio astronomers looked at it. So what the optical astronomers did, because multi-wavelength is so important, they started looking at the stars near Sagittarius A star. So they identified several stars. They're called S0 stars, S01, S02, S0, all the way to 30. And they needed to find out how those stars are moving around Sagittarius A. So what they did was, and it was started in Germany mainly by Reinhard Genzel, they developed a very special camera. And with that camera, every week they'll take one photo. Okay? They'll take a photo with their CCD camera. And then they'll compare week by week what is the position of the stars. See what painstaking work that is? It's such a simple idea, but it's such painstaking work. In that way, they were able to detect the orbits of the stars. So you can see here the little circles. This is one orbit of one star. This is another orbit. Like that, they determine the orbits of many stars. Now, just by determining the orbits, it's very difficult to say where is the center of the potential or what is it due to. You need to use computer simulations. So what they did then was they used the theoretical models of Jeans, a scientist, very famous scientist called Jeans. They used his models and other classical mechanics models to create a model of the center potential around a black hole. And then they put their stars in those models, and then they were able to identify what is the mass of the black hole, which is causing the orbits of stars to follow those particular trajectories. So you see, it's such a broad combination to get this fantastic result. For the mass and position of the black hole in the center of the galaxies, they had to use, number one, theoretical models, which were at least 200 years old, and of course other new theoretical, more programming, simulations. So theoretical models, simulations, and then instrumentation. The camera that they developed, the spectral camera, was so sophisticated that only several years later, these companies like Konica and Sony, they could replicate and use those technology. Because the first technology will always come from pure science. And then that technology is often used in the real day world. For example, our internet. The web was developed by a particle physicist and was developed by scientists working in labs to enable them to have computers to talk to one another. So you see, this endeavor to find the black hole and its mass took so many different types of talent and different types of facilities. Now, this one, I think, this I just want you to see that it took 15 years of regularity to get the first estimate of the black hole. And they're still doing it. They're still doing this, and they are now doing it for many other black holes in very nearby close galaxies. Now, let me move on to the other discovery about black hole, which is the black hole at the center of the nearby galaxy called M87. Now, this is just a cartoon picture, it's not real, but what it's showing you is, this is, for example, the black hole, okay? And the black hole mass comes close and close to the black hole, and it gets shredded tidal force, right? But the black hole is usually spinning, and matter will always have some angular momentum, right? Angular momentum has to be conserved. So the matter, when it comes close to the black hole, will form a disk. It will start rotating around the black hole in a disk. Now, when the matter is in the inner edge of the disk and it falls into the black hole, it will give out radiation. E is equals to mc squared. And that radiation we will be able to see at millimeter radio frequencies. So, this was the theory that was used to detect the inner edge of the accretion disk around the supermassive black hole in the nearest elliptical galaxy M87. What the astronomers did was they looked to find, they can image this inner accretion disk. Inner accretion disk. And that inner accretion disk you can only image in radio frequencies. But here again you had a lot of talent that was required. Okay, I didn't. Let me just finish. So to detect, actually even the inner accretion disk of our galaxy has been detected, the Milky Way. Mass falls into it, gives out some emission, and we detect it in radio. But that radio needs enormous sizes. And you don't have such big telescopes. You can't make them. So what they did was, they put one telescope in the US, one telescope in Australia, one telescope in Hawaii. They used telescopes all over the world. And as the Earth rotated, the telescopes were able to take pictures of that accretion disk. And all the pictures, because with each telescope you get only part of the picture, but with computers you can stack them one by one. They were able to get a good image of the black hole. So if you go back, I don't have an image here, but if you go back and see on the internet the shadow of the black hole in M87, if you do a Google search, a black hole shadow, you'll find that people have done it for 2 galaxies at least, and they're doing it for many others. Any questions about the black holes? Yeah. Yes. So sometimes when matter falls into the black hole, it has to conserve angular momentum. So then it throws out material as a jet. And that jet usually, because it emits in radio wavelengths, it's called a radio jet. No, there are some cases for optical jets, but that's very few. Very few. So I would say only 1% are in optical. No, because it's coming from the inner edge of the accretion disk. Yes. The jet comes from the inner edge of the accretion disk. But the interesting thing, and why research looks at it a lot, is not all black holes give out jets. Only 20% of black holes give out jets. Why the others don't give out jets, we don't know. We think it could be our problem that we can't detect them, that they are there, but we can't detect them. But it's still not very clear. Huh?
Density of this black hole.
Density, I don't think you can. Yeah, I guess if you take the mass and the area, you can do a density. But since a black hole, we don't know what, it's a singularity. A density doesn't really have much significance. Yes, this actually a very, a scientist who was part of the Event Horizon Telescope, he told me that, and I didn't have pictures here, you can make out that it's coming from the inner edge of the accretion disk and it is associated with the black hole. I'll tell you why, okay? You may have seen those, what's called Interstellar, that movie. You should see it. So in Interstellar and in other pictures, you'll see the black hole, you'll see a disk around it, right? Like this. And then from the behind, you'll also see a disk. You'll also see emission coming from behind. Here. It happens because light, the gravity of the light the gravity of the black holes bends light. So we are able to see the back of the black hole, accretion disk, as well as the front. And so those simulations were done by a very famous Kipthorne and Wheeler. Yes. Yeah. Any more questions? Anyone has any more questions? Then we'll do something little boring called galaxy classification. Okay?
As explained,
Yes, Hawking radiation, yes, that's good. Okay, so let us now quickly do something called galaxy classification. I'll just, this is a little bit, doesn't have a lot of science in it, it is just classification. We know that there are spirals and ellipticals, but the spirals themselves are divided into barred spirals and unbarred spirals. A barred spiral has what is called a bar in the center. This is, it looks like it's like a long structure in the center. Those are the barred galaxies. A bar, just like the spiral arms, is due to a global instability in a self-gravitating disk. You can't avoid it. A galaxy will be rotating like this. It will want to form a bar so that it can become stable. So it's a stabilizing influence. So you have barred galaxies, unbarred galaxies, you have elliptical galaxies. This whole classification scheme is called the Hubble tuning fork. And it's called Hubble because, of course, Hubble made it. So we follow this because it doesn't really show anything physics, but it's a very good classification scheme. Okay, and I will skip over this. And the multi-wavelength observations I've talked about, so I think I'll skip on that. Now, why do galaxies appear bright? Why do we see them as bright? We see the galaxies as bright because they are forming stars. Okay, and that star formation gives out light because of nuclear fusion. So over here in this image, you can see here beautiful star forming spiral arms. Okay, and these spiral arms move around a galaxy disk like a wave. Okay, so you can imagine a wave, like just like the wave you see at the beach. But now imagine a wave that is moving in a disk like this, moving around. Okay, so this is the spiral density wave theory. This is how astronomers explain the existence of the spiral arms. And you have often spiral arms triggered by tidal effects, which you can see in this very famous galaxy. And this is an image of the barred galaxy. I just spoke about the bar. The bar, like a spiral arms, is also a stabilizing influence on the galaxy. Now, why does star formation happen in interacting galaxies? That can be explained very quickly. Any system we know in nature, if it is given a little push, a change, a small change, in physics we say it's a perturbation. Okay, it's a perturbation. Now suppose if I take a galaxy which is nicely moving in circular orbits and I bring another galaxy nearby, its gravitational field will affect this galaxy. It will affect it by a tidal force. When the tidal force affects the galaxy, all those nice circular orbits will get affected. So just like you have traffic jams on the highway, you will have clouds colliding and not moving, clustering. The clouds, like they will jam up together, they will collide. When gas clouds collide, they will shock the gas, and the shocked gas will cool and start forming stars. So this is the basic theory about cloud collisions forming stars. I've said it very quickly. I hope if anyone has questions later on, please come and ask me. Now, star formation is usually associated with dust. So whenever you see these dark patches in between the spiral arms, you should remember that these are due to dust. Okay? So you can see here, there's like a band of dark material here. That darkness is due to dust because dust scatters out the light and you can't see it anymore. Okay, so dust always goes with star formation. Galaxy evolution happens due to this interactions of galaxies, which I'll talk about a little bit later. So before I now finish about galaxies, let me talk about how galaxies cluster, because you should know how the universe looks on a large scale. Because in this conference you have been told about star formation, planets, our solar system. I now told you about galaxies, that stars are within galaxies. Now galaxies themselves also cluster, and the galaxies, they can cluster in pairs. They can cluster in pairs. So we have pairs of galaxies. Andromeda and our galaxy practically form a pair, very close to one another. Then groups of galaxy groups, 3 to 50 galaxies can come together and form a little group. So this is like a bit like people, we get together and we form associations. We can form larger associations, which are called clusters. Galaxy clusters are huge structures in our universe. They can contain about 1,000 galaxies, few hundred to 1,000 galaxies. And finally, we have galaxy superclusters. So we're going from galaxies to galaxy pairs, then galaxy clusters and groups, and finally to superclusters of galaxies. Now, this is an image of a galaxy group, a very famous galaxy group. I just wanted to show you that. And this is a picture of a galaxy cluster. This is also a very famous galaxy cluster called the Coma cluster. You can see how beautifully it looks in the optical image. Now, if you look at it in X-ray, you see this. You see this huge halo of X-ray emission, because usually galaxy clusters have a large halo of X-ray emitting hot gas around them. These are called their X-ray halos. So as you can see here, again multivariate observations become extremely important. So now after all this clustering, which was known many years ago, in the 80s and in the 90s, when people looked at our universe and looked, with very good cameras very far, what they found was that you have these fantastic superclusters. This is a supercluster, you can see here. It's a collection of many, many galaxy clusters. Okay? And here it forms like a wall. And at the bottom here, this is also called a wall. You can see a little man. And some people also said this was like the finger of God, which I find very strange. But so this is showing you that the universe on larger scales has a structure. And that structure is composed of walls and filaments of galaxies. And it all forms what we call the cosmic web. The term you may see sometime in the common science discussions, the cosmic web. Cosmic web is nothing but the whole universe structure of galaxies and superclass galaxies and empty regions like this here, which are called voids. So you have galaxies and superclusters of galaxies, galaxy walls, and finally you have empty regions called voids. So this is the large-scale structure of our universe. And this is our neighborhood, the local galaxies that we have in our neighborhood. Andromeda is over here. Andromeda is here. Milky Way, our galaxy is here. The little Magellanic clouds that I talked about are over here. And then we have a whole host of very small galaxies, which we call the satellites. They're called the satellite galaxies, which are near us. They're small, we don't always see them. Okay. So before I move on to galaxy interactions, I want to talk about Hubble's law and redshift. Many of you may have heard of this, that our universe is expanding. Okay, some of you have, but those of you who have not heard, let me just explain that more than 100 years ago, a scientist, Hubble, what he noticed was when he looked at the galaxies which were near our universe, he found all of them are moving away. Okay, and so he made this plot. He found using spectroscopy the distance of the galaxy. So this is the distance. And he plotted using the Doppler shift of the lines, what is the velocity of recession. Okay, so we plotted distance and we plotted velocity. And what we found is this guy's correlation. So what it means is the further away you go from our galaxy, the faster things are moving away from each other. And that's really, it's difficult to comprehend. Now we're used to it. But if you think of it, it's very difficult. Everything is flying away from everything, right? Where are we all going? But this is very important part of cosmology. It shows that our universe is expanding, expanding according to the Hubble's law. And that has been followed up by decades of research, and we find that that expansion is still there, like this. It's not expanding and closing. It's just expanding, slowly expanding, but it is expanding. And this is the Hubble's law. So a good way to think about it is, you imagine that you're making a cake in an oven. This is given in all the textbooks. It's not just my idea. Imagine you're in a cake and the cake has got raisins in it. As the cake bakes, right, everything moves away from it, right? All the raisins are going away from each other. Okay? That is the Hubble expansion. When everything, you're a point in the cake, and as the cake bakes, everything moves away from a particular point or a particular raisin. That is the Hubble expansion. The law of recession. Huh? By what? Big crunch. Okay. Yes. Yes. So the Big Bang theory has shown that there will be an expansion. There will be some inflation after the initial singularity. Then the universe suddenly expands, and then it keeps on expanding. So what you're saying, the big crunch, is that according to some theories, we will expand and then we'll collapse, right? But from observations, we find that the big crunch is not happening. We are expanding, not exponentially, but slowly. There is no big crunch. That's what observations indicate. Some people still believe in it, but the data that we see right now suggests that the big crunch is not going to happen. That our universe is expanding steadily at a constant rate. I don't think it will happen like that, because if it's just expanding, there will be no end of the universe. Yeah, I think there's no end. The universe is infinite because it just keeps on expanding. So, any more questions on all of these topics? Yeah, tell me.
How is second law of is there any relationship between second law of like he's talking about when
so second law is this energy, entropy. So in the second law, we think that entropy must always increase.
So people, they connect that time is in one
direction.
And the same way the universe expands
one direction.
This is follows he's talking about something like
crunch.
Something like that. So
second
law thermodynamics.
Yes, I think he's just answered your question. That if you had a big crunch, maybe second law of thermodynamics, where we think that entropy will always be increasing, that will be violated. Okay, so we think that entropy should always increase, which happens also in galaxy mergers, the entropy increases. Yes. Heating and expanding. Okay, so now let's go to little bit more mundane, more ordinary concepts of galaxy interactions. I won't take long. This is an example of some work I did with my students. You can see here two galaxies are very close by, and this has got nice spiral arms. This is an infrared picture. So this picture is telling you about the stellar structure. You can see the stellar structure here, and there's a small galaxy that is kind of merging with this galaxy over here. So this is a good example of you're having galaxy interaction and you're also having galaxy mergers. Okay. So galaxies evolve due to mergers, galaxy mergers, but they can also go past each other, in which case they have galaxy interactions. So let's suppose one galaxy and another galaxy goes past it. Then when it goes past it, it will perturb its gravitational field. Gravitational field was nice and axisymmetric. Now it will get some gravitational perturbation, delta phi, and the non-axis symmetry that will result, it will cause cloud collisions and star formation. Now suppose that flyby interaction happened, but the small flyby galaxy came back round again and it went in orbits like this, and finally it merged with the large host galaxy. So from a distant interaction and flyby interaction, it has become a galaxy merger. So these events are very common because, as I mentioned earlier, gravitational forces will result in galaxies interacting and merging. These are some very beautiful pictures of galaxy mergers, and you can see here very clearly that as the galaxies merge, you can see their nuclei here. These are their bulges which contain their supermassive black holes. So as galaxies merge, their supermassive black holes also come closer and closer to each other. That's one topic that I also study with my students. So why is it important? It's important because these mergers of galaxies result in galaxy growth. So when two galaxies merge with one another, you will have a lot of star formation, but you will also result in the formation of a larger galaxy. So in cosmology, what we think is that the universe started with galaxies, but the larger galaxies were created by galaxy mergers. We call the term that's used is hierarchical growth of structure. Hierarchical means that from smaller to bigger, we have grown galaxies in our universe from smaller to bigger. So galaxies grow, and when they grow, they also evolve, they change. Evolution is a kind of change. So I'll skip this one because that, yeah. So this is it's a very complicated picture, but it kind of shows you the whole structure of this evolution and mergers. So you can start with, say, molecular clouds in galaxies. Then there's a cycle of star formation, supernova, stellar mass loss, gas cooling. In between, you can have some nuclear activity, which will give out jets and winds, give out outflows. All of this cycle of activity will result in galaxy evolution. But it will also be more powered if there are galaxy interactions and mergers. Now, finally, what happens when galaxies merge and we see all this merging phenomena is that galaxies evolve or they become older. So in the last 20 years or so, there has been especially one very important telescope and service called the Sloan Digital Sky Survey, or SDSS, and that has looked at images of millions, I think millions of galaxies, 2 million to be exact. And what they find is that galaxies, after they merge, they grow old and become red. They fall into this red cloud. And the galaxies which are very young and still forming stars, they are in the blue cloud. So this kind of a sequence is called the color magnitude plot for galaxies. This shows that galaxies will change, evolve from the blue cloud using star formation and galaxy mergers, and finally change into the red sequence or red cloud. So this is actually a kind of a diagram that shows the evolution of galaxies. Because as you know from earlier studies, for most sciences, we want to see a path. If we know that there is change, we want to see the path of that change, and we want to see the end result of that change. It has been seen for stars because stars have a HR diagram. Okay, there's a main sequence, a Hertzberg-Russell diagram for stars is there, their evolution. This is a similar evolution plot for galaxies. Okay, so this is my summary. I think I stopped on time, but I can take questions. Let me just read out the summary. Galaxies, please remember, is large collections of stars. And when I mean large, I'm talking about millions and billions of stars. And galaxies have their own classification scheme. There is a tuning fork, and the tuning fork has ellipticals on one side and spirals on the other, barred spirals and ordinary spirals. Multiwavelength observations are very important for understanding galaxies. And galaxies and interaction and mergers lead to the growth of larger galaxies and redder galaxies. I haven't included the black hole here because I think I just put it in my slides, so I don't have it in the summary. Thank you. Any questions that I can answer? Big Bang Theory.